So this is actually a repeat slide because I want to emphasize the three types of way the atmosphere can be, is the way I think of it. And the atmosphere can either be absolutely stable, absolutely unstable, or conditionally stable. And in each of these cases, we're talking about a parcel of air. Will the parcel of air, like you see at the top here, will it be stable? Will it have a tendency to drop because it's colder than its environment? Or will that parcel of air be unstable? Will it have a tendency to rise? And if it has a tendency to rise, it's going to have a tendency to rise to be buoyant, not a lifting mechanism, but an unstable parcel of air will rise because it's warmer than the environment, just like those hot air balloons. So starting with absolutely stable or absolute stability. In each one of these cases, the way the atmosphere is, whether the atmosphere is stable, unstable, or conditionally stable, it has to do with the environmental lapse rate. And you're going to see a figure here to remind you what the environmental lapse rate is. But the environmental lapse rate is basically when you send up a weather balloon and you get what we call a vertical temperature profile. So if the environmental lapse rate, you send up a weather balloon, and if it is less than the wet adiabatic rate, now I'm going to have to kind of talk about what the wet adiabatic rate is. But if that's the case, then that parcel of air, as it rises, will tend to always be colder than its environment. Its environment will be warmer. And so if its environment is warmer, your parcel of air is colder, it will be stable and have a tendency to fall. And that's exactly what we're going to see in the example we're going to look at. If the environmental lapse rate is less than 5 degrees Celsius per 1,000 meters. So let's see. We're going to look at an example here, and it's going to really help a lot. So in each of these cases, we're going to look at the environmental lapse rate, and we're going to compare it to the wet adiabatic rate, the dry adiabatic rate, and you'll see what I mean. Now, a temperature inversion, as it turns out, if we have a temperature inversion in place, actually that environment then is very stable. And for this same reason I'm going to show you. All right, so this is showing you basically this atmosphere is going to be stable, and so it must be less than the wet adiabatic rate. Okay, and actually I'm going to show you the forced lifting mechanism here is a frontal lifting mechanism, in that we basically have a cold air mass over here on the, I guess it would be over here in the camera, but it's on our right. And warm air is being lifted up and over that. Okay, so the environmental lapse rate must be less than the wet adiabatic rate. Now I'm going to have to let you know that the wet adiabatic rate of 5 degrees Celsius per every 1,000 kilometers that a chunk of air rises if there's condensation going on, that's the rate it cools at. Actually, your author now kind of switches gears just a little bit, and the wet adiabatic rate is now 6 degrees Celsius per 1,000 meters that a chunk of air in which condensation is going on will cool. And I'll show you what I mean by that. But let's say we send up our weather balloon and we get a environmental lapse rate. This is our ELR, our vertical temperature profile of cooling 5 degrees every 1,000 meters that you ascend, the balloon ascends. So if it starts at 20, then it must go to 15, and then 10, and then 5. You know, each one of these lines is 1,000 meters. So then it goes to 0 and then to -5. So that is the vertical temperature profile. So here's where I need to warn you that instead of a wet adiabatic rate of 5 degrees Celsius, your author, and you're going to see it on these slides that these examples, we're going to see that if condensation is happening in the parcel of air that's ascending, then the wet adiabatic rate it's going to cool at now is 6 degrees Celsius per 1,000 meters. Okay, so that's the balloon. The environmental lapse rate is cooling 5 degrees Celsius for every 1,000 meters. We're going to go with beyond the lifting condensation level, where that chunk of air is forced to rise. It's going to cool at the 6 degrees Celsius per 1,000 meters. Okay, so here we go. Here is our cute little parcel of air, and when it's at the surface, it's the same temperature as the surface, which is 20 degrees Celsius. It has a forced lifting mechanism, cold air mass, and so that chunk of air is forced to rise, and as long as there's no condensation going on, it will rise and cool at the dry adiabatic rate. No confusion there. Dry adiabatic rate, 10 degrees Celsius for every 1,000 meters it ascends. So the first 1,000 meters it ascends, notice that it cools from 20 to 10 degrees Celsius. Now, to check the stability of that parcel of air, what you need to do is compare that temperature, the 10 degrees Celsius, with the 15 degrees Celsius, the temperature outside that parcel of air. And since 10 degrees is cooler than 15 degrees, even though we have a lifting mechanism going here, it's a type of frontal lifting, or wedging, frontal wedging, I think your author calls it, that has a tendency to, that 10 degrees chunk of air has a tendency to want to fall in the warmer environment. So let's go up from 1,000 meters to 2,000 meters. And there's no condensation going on, so it's going to cool at the DAR, the dry adiabatic rate, 0 degrees Celsius. Okay, now again, let's go ahead and see what sort of tendency we have. If we compare that parcel of air, which is 0 degrees Celsius, with its environment, notice it's still cooler. Okay, so its tendency is going to be down, even though we have this wedging going on. All right, we're going to have it go ahead and notice, I don't know if you can kind of see, but we have reached the lifting condensation level, the LCL. That parcel of air has cooled to the point, the dew point temperature, and we have condensation happening. And so now notice when it rises from 10,000 meters, from 20,000 meters to 3,000 meters, from 2,000 meters to 3,000 meters, notice that it's going to cool at this wet adiabatic rate of 6 degrees Celsius per 1,000 meters. Okay, now let's take a look. Let's see, -6 is cooler than 5. Okay, so it's still got a downward tendency. It's stable. That chunk of air is lifting, but it's stable. The next 1,000 meters, it's going to cool another 6 degrees. So now it's going to go from -6 to -12. If we compare the temperature of the parcel of air at 4,000 meters to 0, it's still cooler. And one last little step there, at 5,000 meters, we've got parcel temperature that is definitely cooler than its environment by 15 degrees. So in each one of these cases, can you see where basically we have this is the tendency, okay? So this is a stable environment. This is absolutely stable. This will always be the case if, like I said, if the environmental lapse rate is, what we say, less than the wet adiabatic rate. Okay, and we're going with a wet adiabatic rate of 6 degrees Celsius for every 1,000 meter that chunk of air rises or is forced to rise. So if we kind of look at the purple is the environmental lapse rate. You can see how the temperature is cooling as it goes up in elevation. And over here then is the temperature profile of the rising parcel of air, where the red, you can see it's rising, it's cooling at the dry adiabatic rate, and then the blue is it's cooling at the wet adiabatic rate. But in all cases, can you see where this is the parcel, this line over here, the red and the blue is the parcel, and in each case the parcel is going to be colder than the environment outside the parcel. Okay, if that's the case, the tendency is to not rise. Okay, so this is just to kind of show you that I'm not losing my mind. This is a figure earlier, and we said that the wet adiabatic rate this is from the same textbook, that the wet adiabatic rate is 5 degrees Celsius per 1,000 meters. And then more recently, we have this slide where the wet adiabatic rate is, the WAR, is 6 degrees Celsius per 1,000 meters. I did just a little bit of checking, and I've seen both of those as the wet adiabatic rate in the literature. So, hey, it all works out. All right, so what happens if we have an atmosphere that is unstable, absolute instability? And actually, if you're one of those storm watchers, you know that that meteorologists will, when we have thunderstorms, talk about the atmosphere as being unstable. So you will have an atmosphere or environment that is unstable if the environmental lapse rate, the ELR, is greater than the dry adiabatic rate. And the dry adiabatic rate is that 10 degrees Celsius per 1,000 meters that a dry parcel of air that no condensation is happening in will cool. So we're going to look at an example here. Environmental lapse rate, send up your balloon, and your atmosphere is basically cooling faster than 10 degrees Celsius per 1,000 meters. What that means then is that as your parcel of air ascends and cools, that it is always going to be warmer than the environment. Okay? And if that parcel of air that's ascending and cooling is always warmer than the environment, then it's going to be buoyant, and it's going to be less dense, and it's going to shoot to the moon. Okay? Your environment is said to be unstable. It'll keep rising. And I'll show you an example here. If the environmental lapse rate is greater than 10 degrees Celsius per 1,000 meters. So this is an absolutely unstable situation. We have absolute instability here in the atmosphere. And so notice you send up your weather balloon, and your environmental lapse rate is greater than 10 degrees Celsius per 1,000 meters, that you go up in elevation in the troposphere. And here we're going with 12. Let's see what kind of consequences that has. So if our ground temperature is, or surface temperature is 40 degrees Celsius, actually that's going to be the temperature of our little parcel of air as it starts. So our weather balloon went up then, and if you take 40 minus 12, you get 28. 28 minus 12, you get 16. 16 minus 12, 4. 4 minus 12, negative 8. So this is going up every 1,000 meters. It's getting cooler by 12 degrees Celsius. All right. So here's our cute little parcel of air. And notice we have a different lifting mechanism. This would be convective lifting, wouldn't it? So here we have our little parcel of air. It's going to start to rise. And notice that first 1,000 meters it rises, it's going to cool 10 degrees Celsius. Now let's look at its tendency. To know its tendency, we compare the temperature of the parcel of air, which is 30, to the temperature outside, which is 28. Ooh. Since 30 is warmer than 28, that thing's going to want to keep going up. Let's see what happens when it goes up to 2,000 meters. Now your parcel will now be at a temperature of 20 degrees Celsius, and we can compare that to 16 degrees Celsius. Ooh, the temperature difference just got even larger. So that means it even maybe wants to accelerate? I don't know. So let's see what happens when we reach the lifting condensation level. So you can kind of see the fluffy clouds form right here at 2,000 meters. So from 2,000 meters to 3,000 meters, we're going to have condensation going on, and it's going to cool at the wet adiabatic rate of 6 degrees Celsius for that chunk of 1,000 meters. So 20 minus 6 is 14. So 14 degrees Celsius is the temperature of this parcel of air. I don't know how big we want to make it, at 3,000 meters. Now let's compare that to the outside temperature. Do you see what we have here? That's a difference of 10 degrees. Whew. Okay, so that's even more wants to rush up. And if you've watched thunderstorm develop before. You know, the real scary ones are the ones that kind of bloom and you get this what we call vertical development kind of quickly, and that's kind of what we see going on here. So 1,000 meters up, you take 14 minus 6, you get 8. So that's the temperature of that parcel of air. If we compare 8 degrees to -8, you've got a difference of 16 degrees Celsius. Okay, so basically what we've done at all elevations is to say our parcel of air is going to be warmer than its environment. So that's why its tendency is to rise. We would definitely call that chunk of air unstable. The atmosphere is absolutely unstable. And why? It all has to do with the environmental lapse rate. When you send up that weather balloon, what is the temperature profile? So we have one more possibility. Oops, let me show you this. All right, so the blue line here is what the temperature profile of the environment. And here the red and then the kind of aqua line here is what our parcel of air temperature is. And so can you see where our parcel of air is always, I guess it's this side, our parcel of air is always warmer, than the environment. So to the moon, well, not really to the moon. So the last situation is we have something called conditional instability. And what you're going to see is that the environmental lapse rate is between the wet adiabatic rate of 6 degrees Celsius. I'll go ahead and put a 6 in there. And the dry adiabatic lapse rate, so dry adiabatic rate of 10. Okay, 10 degrees and 6 degrees. So that kind of gives you a range for the environmental lapse rate, and we'll get conditional instability. And I'll kind of show you why that is. But basically, we're going to see that it will tend to rise until it becomes saturated, and then it will have the tendency at some point to go ahead and want to to fall because it's stable. Okay. So let's look at an example of that. All right, so this is conditionally stable or conditional instability. Conditionally unstable? I don't know. But what you're going to see is that we send up a weather balloon, and remember that the environmental lapse rate, here's the ELR up here, it needs to be between 6 and 10. And here your author has it at 9. That fits the bill. So our surface temperature is 40 degrees Celsius. If we subtract 9 from that, we get 31. 9 from that, 22. 9 from that, 13. 9 from that, 4. And 9 from that, and we get -5. So that's how the temperature of the atmosphere is cooling as you go up in elevation. So again, we have this sort of wedging, frontal wedging situation where air is being, that's the lifting mechanism. So let's look at our parcel of air. It first is going to rise at the dry adiabatic rate of 10 degrees Celsius for every 1,000 meters. It is forced to ascend. So at 1,000 meters, we see that our parcel of air is just a little bit cooler than our outside temperature. Okay, so that looks like it might have a tendency to want to fall. Let's go up another 1,000 meters and notice then that we have it cools from 30 degrees Celsius to 20 degrees Celsius, and again now we've got a difference of 2 degrees. This is cooler. Okay, and what does that mean? Then it'll have a tendency, this sort of tendency. Okay. So, but now let's go ahead and pass the lifting condensation level. Can you kind of see some clouds forming there at 2,000 meters? This is the LCL. And if we have condensation, then the cooling as it's forced to rise will now cool at 6 degrees Celsius for every 1,000 meters that chunk of air rises. So the first 1,000 meters it ascends, notice now that it goes from 20 minus 6 is 14. So the temperature at that elevation is 14 degrees Celsius. Now if we compare that to the outside temperature, it's warmer. Okay? We now have a tendency to rise. Let's go up another 1,000 meters and it cools another 6 degrees down to 8 degrees. And notice now 8 degrees is 4 degrees warmer than the environment. It even has more buoyancy. Okay, go up to our 5,000 meters and it cools from 8 to 2 degrees compared to -5. Oh, we're looking at a 7 degrees difference where their chunk of air, your parcel of air, is warmer. So actually, do you see where condensation begins? The tendency then changes to becoming unstable. Where there was no condensation, the tendency was for stability. So if we look then at the profile, the temperature profile, it's kind of a mixed deal. It's conditional. It's conditional whether there's any condensation or not. So it's a little bit tight, but if you can see that purple line, I guess it's purple, not blue, isn't it? That purple line is the environmental lapse rate, what the balloon information that the weather balloon gave us. And then the red line down here is the cooling of the parcel of air where no condensation is occurring, according to the dry adiabatic rate, the DAR. And notice in this case, it's just a little bit, the red line, the temperature of the parcel is just a little bit cooler than the temperature of the atmosphere. Okay, that gave us a downward tendency. Then here we have the lifting condensation level, about 2,000 meters. And now we have this blue line here, where can you see at some point our parcel of air then is warmer than the environment. And there you have it. Basically, that's where it picks up the tendency to be unstable. So stability is conditional upon condensation or no condensation. And you'll get that if the environmental lapse rate is between 6 and 10.